Okay, so today's lecture will be mostly on networks of oscillators. This might look like a bit abstract. What are these networks? What is this oscillators? But to motivate you, I will show you some videos so that we can start off the lecture in a smooth way, and then you can appreciate whatever is coming in the next slides. So let us see, yeah, is in. I've already kept it here. I think Dikhil already have showed this in one of his classes, but I want to show it somewhat more. Let us see this one. So you can see in this video that there are two oscillators, and both are metronomes. Like they will just move together in a tick tick manner, but both of them are totally different, right? Both are two different entities. Yes, but there is one thing which you don't realize. There is one thing which you don't realize, which I'll ask you. Okay, so let us run this and see. Yeah, can you observe something that previously they were not in sync, but as time progressed, they got in sync. Okay. Now I think, yeah, now they're in perfect sync. Okay. Previously they were not in sync. So this is not any two oscillators. Rather, this is true for as much as you want, like how many oscillators you want to keep. Okay. So why this is the case? Can anyone tell me? Initially they started out of sync. Now you see they are totally out of sync. But within few seconds, they will be in sync. Any ideas? Like without any knowledge of physics or anything, just if someone you ask, I will pause it. I'll pause it. See, this is a very nice thing. Like I can pause it at any time, and you can see that the angles in which they are is will be almost the same. Okay, you can see now I paused at a snapshot. This is at a particular time, and you can see both of them are at the same angle, almost the same angle, isn't it? So you can see they are perfectly in sync. Now let us take some other snapshot. Like, yes, now also you can see that they are also in sync. All are lying in this way. All are lying in this way. So whatever snapshot you take, they are at sync. But my question is why? Yeah, now also they are in sync. Now also. Any small time step you oh no. Okay. Yeah, any time step you take, they will be in sync. Why? Any common ideas? Yes. Yes, that's the most important thing. As you can see, if you could have put one metronome on this table and one metronome on your desk and started at the same time, then they will not be at sync. Okay, they will not be at sync. But you can see in this figure that there are two Coke bottles, that you have a wooden plank, and on the top of it you have two metronomes. Okay, they are oscillating with each other, but you can see that the two metronomes, like, they are very close to each other and share a common boundary. They share a common platform, and that common platform, that wooden plank, helps them to say that, yeah, you go with me, like you oscillate at my speed. So both of them, they participate together in oscillations, and that's how they maintain this sync. Okay, so this is what is known as a coupling. This is what is known as a coupling. Like you can see the wooden plank is acting as a coupling variable. So you can see, like, now if you walk, then consider you and your friend walking together. Okay, so you can see that when you walk together, you can see the footsteps will be in sync. Unknowingly the footsteps will be in sync. Now if you record a video of the side view, then you will see that when you put the front foot ahead, this other guy also puts the front foot ahead at the same time, and therefore you are walking at the same level together. But if someone is unknown in the sense like someone who you never met, he's an unknown guy, then you can see that the sync won't happen that properly. Okay, then you can see that the sync doesn't happen properly. That means it will take some time to understand each other psychologically, saying that yeah, this is a he's a fast guy or he's a slow guy, and therefore I have to match his or her speed. Then after some time you will match with her speed and then continue working together. Okay, so this is one example of sync, right? Anyway, so I think did Nikhil show this one? No, no. Okay, so this is a case in US. In the US, in the states. So what happened is a lot of people gathered in a bridge. Is very famous bridge, like in the sense that this is a tourist spot. Okay, it's a tourist spot, and everyone wants to walk in it. Okay, during their holiday time. So every household wants to walk, but the main problem happened is every household decided the same time to walk. Okay, so this is the case. You will see. This was recorded by a CCTV. Um, you can see it like slowly you can see the bridge, it has been supported by so many beams, but it has started to oscillate. Can you see it? It has started to oscillate. Just see the sideward beams. Can you see it? Okay, so yeah, and people and it is a crowd, no one knows each other, but they are stepping in just like each other, but you can see it is oscillating, the bridge. And this is a sign of great concern actually at that time, and nothing could be done within a short amount of time. Okay, yeah, yeah, okay, no, no, I don't want to. Okay, sorry for the ad. Anyway, unfortunately, after the video clip you just saw, the bridge collapsed. Okay, so this is a great, like this is a unfortunate incident of the Millennium Bridge, and is a great example of why you should need to understand about synchronization. Okay, so if you know in your school days, in your physics subjects, they say that if soldiers are like walking on a bridge. Yes, and you know the soldiers have a stance. They have a particular stance and they follow it. Yeah, every soldier follow it. Okay. So due to that, the frequency happens, the resonance happens. Okay, the resonance happens, and resonance, due to the resonance, there occurs a large amplitude event. And due to that, the bridge might collapse. So this is the examples, and this video will show you one experimental study of the neurons, like biological neurons. So what I have been doing so far, like my area of expertise is mostly simulation, like you can say computational modeling kind of things. But the video you will see now is mostly based on the experimental studies. These are biological studies. You can see petri dish, you can see the microscope in action. Okay, and then you can see that experimentally they have shown that in neurons you need to have synchronization. Like synchronization persists, you don't need to have synchronization, but synchronization phenomena persist in a millions of neurons. Okay, so this is one such example. I think it was done in it was published in the Journal of Neurophysiology, uh, and it is Institute of Occupational Health Sciences. So let us see this one. Um, Yeah. So this is one example where you saw that, yeah, synchronization actually is a practical phenomena, not in oscillators, but rather in your tiny microbial neurons, like which you cannot actually see in action. You need a lot of microscopic power to see them. But you can see that they experimentally found in male rats. So they did this experiment with male rats, and how they could enhance or fiddle with the neurons of the male rats. You want to tell how they were considering, like, yeah, neurons off, neurons on. Like, see, you, how many of you can sleep with lights on? Okay. I mean, yeah, many of them can sleep with lights on if you are really tired. If you're really tired, but usually it's very very hard. Like during night time, if I ask, like, yeah, light is on, you sleep. Then very rare it is. But at one point you will sleep. At one point you will sleep. Your brain will give up and you will sleep. So what they did here in male rats is they put lights on the rat, okay, and they put the lights off of the rat. So when the light is on, then the light receptors, the eyes got that, and neurons can see the signal, okay, neurons can sense it, so neurons were active. When the light was off, then it told the brain that no, now is the sleeping time, okay. So when the light is suddenly on, like I usually get in the morning up by seeing the sunrise. Okay, if the sunlight falls, then I get a impact that yes, it's already morning. Okay, so if the morning happens at 10 a.m., then I have to wake up at 10. It's like that unless my biological clock says so. Okay, so therefore these are the kind of tools for experimental study. Okay, so this is very far away from the simulations what many students have been doing. Okay, what you do is you have a neuron, and luckily due to some few scientists in late 90s or 80s, I would say 70s, late 70s, 1970s, they found a mathematical expression which can tell you about neurons, how the neurons fire and burst, and due to that a lot of phenomena has been seen. Okay, lot of phenomena has been seen. So that's the aim of this lecture. That's the aim of this lecture. So yeah, another way is you have seen your heart. No, no, yeah, you have not seen your heart, but you know your heart is there, and most importantly, when people suddenly get this cardiac arrest, okay. So usually, what is seen in medical studies is the presence of spiral waves. Okay, so you can see the study from Science X. here it is saying that the researchers map these rotating spiral waves in live human hearts. So of course this is an experimental study, but you can see these are the hearts. Okay, so you know already that you just take your thumb like this, and the size is the size of your heart. Okay, so therefore you can see that yeah, it makes sense to show the heart like this in the picture. Okay, and most importantly, you can see the color codes. Normally you won't see these color codes, but these are mapped computationally. Okay, so if your heart, like it's just like thermal imaging, it's just like thermal imaging used during COVID times. So how they were scanning lot of people like on airports, so they had a thermal camera, and each person was walking, and they would scan from top to bottom which part of the human body is showing green, which part of the human body is showing red. And due to that, they can easily feel the temperature. Okay, if they see most of the body part of that person above the chest level is red, that means is having a higher temperature. That means there is a higher chance that he is suffering from fever. Okay, so like that they do it. And most importantly, I if you have heard, I was personally there. So during the year, I think 2019, during the year 2019, I was in Sydney, and in that suddenly we were in one hotel actually, and then suddenly there was a fire breakout in a forest. Okay, so lot of smokes and all we could see. You know that if smokes come, you can see from the top that something is happening. So then the people would know that yeah, there is something fire, like the forest has caught fire, and lot of animals were there, like koalas, bears, and all those were there, and there some were babies. So they were running for their life, and a lot of people suddenly went to the spot and got some koalas like to help them. So, but no one can spot out. No one, and some can go extinct also, extinct. So how can you help those animals in such a short amount of time? Any ideas? Any thoughts? Any thoughts? You understood the problem, right? It is a real life problem. I faced it. But how could you save those koalas? And fire is spreading out. The temperature was so high. The temperature was so high. Like I was sitting in that house in 7 like fully lowest temperature AC. I was not even moving out of the house. You will feel your skin. You will feel that the sunlight is entering. It is that intensity because those regions, the countries near the ocean, okay, they are very prone to get UV lights. Okay, so therefore usually you see they apply sunscreen and go. In India it's not that necessary, but yes. So in countries in the specific, you have to apply, else there is high chance that you get UV in your screen. So how can you reduce, like how can you bring those animals back to safety? There can be persons also. Usually they do hiking, climbing forest or climbing mountains. So persons can also be tracked. How can you do it? Any thoughts? Yeah. So after a while, since Australia saw that this is a usual case, every year they are noticing fire in wildlife. So one of the things they did is the help of drones. Okay, what they did is through drones they went up. Okay, through drones, the drones went up. Many drones they went up, and the drones were capable of thermal imaging. Okay, so those areas, if the koala is moving, they can see, it is a real-time video. They can see that the koala is moving and the koala is at a higher temperature. That means the fire is there. And even the trees are burning there will have the red parts. Okay, so they will know through a snapshot that yeah, these are the parts where fire is not there. These are the parts where a lot of fire is there. So they will know which area to go, and Google will give you the coordinates where to go, which part of the forest. So without any loss of time, they can go to that region and save the koalas. Okay. So this is one real example of this thermal imaging. So why I said this is you might get confused that heart looks like this, but it's not. So let us see this. Actually, this is a case. This is the case of a experiencing cardiac arrest. Okay, which is experiencing cardiac arrest. And this is the time series below you are seeing. Yep. So you can see on the figure on the left, you can see on the figure on the left that it is rotating spirally. Can you see it? Can you see it? It is leaving, it is going out almost instantaneously, but you can see that it is having a rotating frame. It is having a rotating frame, isn't it? Shall I play it again? Mm. Yeah. So can you see this figure? See this, this is the center of the spiral. See my mouse cursor. This is the center of the spiral. And you can see that it is rotating like this. It is rotating almost like this. Okay. So yeah, I think only I think 3 students are there who have done this. We have seen this actually in simulations. So yeah, you can see the time series also. Okay. Fine. So this is one such model where in heart, okay, heart is beating, okay. So who told about Vanderpool oscillator in the project? Who told? Yeah. So Vanderpool oscillator, you can see if you go more deep, you can see that the Vanderpool oscillator is actually can be modeled in terms of a heart, okay, because there is a fast and a slow dynamics, and heart also has that, okay. So you can search like Vanderpool oscillator and cardiac models, so you can get a feeling that you can approximate the heart dynamics of the heart in terms of that Vanderpool model, okay. So yeah, so I want to say that these spiral waves you are seeing is important in hearts as well as in your neurons, okay. You can see the heart, the structure of the heart is actually 3D, but it is very difficult to construct all this. But what you see now is a slice of the heart. Okay, that is a 2D. Okay, fine. Now another example is in Thailand. Like in Thailand, like we don't see in India here because I don't know why, but ecology people can help me explain better because I have seen fireflies here mostly during Diwali time. Okay, fireflies come mostly during Diwali time, but I have seen lot of fireflies during Diwali time in my home, nearby my home when I was a kid. Okay, after lot of years, I don't see them. I think it's mainly due to global warming or something. They are going extinct. But in Thailand they are prominent. In Thailand they are prominent. Yeah, so also there is a very nice song of fireflies. How many of you have heard Fireflies song? No, no. Should hear Fireflies. Very nice song. So anyway, uh, just see this. So this is taken during the night time, and can you see? Can you see some dots? Any bright dots you see is a beat of a firefly. Is a male firefly trying to attract the females. Okay, you can see this. So and it's real. Like it's just like side is the LED bulb. I think. Hmm? This is a marvelous phenomenon. Like who it's like this, and they are not even communicating with each other. Like, and everyone is in a competition. Yeah, so these are all like fireflies in a tree, I think. So this is what you see. Those students who have worked actually with networks, or yeah, you will know. Yeah, so this is yeah, some forest in Thailand. Okay, so quite a good phenomenon actually. So you can see there's some flash, some be in rest, but you see a pattern. You see a pattern in them, isn't it? So yeah. So this is what fireflies are doing. They are not even connected with each other. Okay, but they are connected in some way. They are connected in some way. Okay, because each firefly can know that this firefly is flashing. So he feels a bit bad. He also flashes. Okay, fine. So, now you saw a lot of real life phenomena where synchronization, and all these factors are seen. Okay. Now, after all these phenomena is seen, what the scientist does is I can understand this. That's the first question he tries to ask. Okay. So this was done first by Kuramoto. Okay, Kuramoto, which I'll show you now. Okay, he is a Japanese scientist, and he created a mathematical model which can model all these phenomena in one equation. Okay, let us see this. So this is known as the Kuramoto model. Yeah, his full name is Yoshiki Kuramoto. So this is a mathematical model for describing synchronization aspects. You can see that it is a model which can help you understand the behavior of a large set of coupled oscillators. Okay, you can see, you can imagine each of these fireflies as an oscillator. Oscillator in the sense that they are showing light, then blinking. They are blinking, in fact. Okay. So you can see that even in chemical or biological oscillators, they are helpful. I have shown you one chemical oscillator also, which was developing the spirals, if you remember. Yes, I think it was the first class. Anyway. So you can see these are neuroscience and also in oscillating flame dynamics. So I will tell you one example to do at your home. Like if you have candles, if you can get some candles, put the candles nearby. Okay, put the candles, three candles nearby in a circle, like, or in any topology you want. Okay, and light them up. They should be very close to each other, like this. They should be, this is one candle, this is another candle, another candle. Okay, put them together nearby and light the flame in each of them. Okay, then you will see that what you expect, what is your mind tells. All the flames will be the same. What do you think? Is it? You do this study. Okay, then what you do is you should make sure that there is no fan, there is no external disturbance like wind and temperature difference and all those things. Okay, so, and another example I will give you is keep one candle here and one candle very far, three candles far away, and light them up and see what happens. Okay, so in the case that there you will see different types of phenomena there. Okay, and it is a very common thing, no, it is very common practical thing, but this study got published in Nature, which is very top journal. But he studied that synchronization phenomena, like how one, if one is lighting, it is creating a swirling pattern, and how that is affecting nearby candles. Okay, so you will see one flame is up, one flame is down. After some time, you will see that flame goes down, this flame goes up. And after a bit of time, you will see the both flames are same. So that's like synchronization. But anyway, how this model looks like? So this model looks like this: d theta I by dt. So yeah, maybe this is very sudden. I don't think you can get the concept quite easily just by looking at this equation. But what I will say to you is just see this here. Okay. Um, Yeah. So what he did is he took a circle and he put lot of points, lot of oscillators on the circle, on the boundary of the circle, and let it evolve, like let it flow. They cannot go anywhere. They have to be on the circle only. Okay, so you can see that after a while, like these are the coupling strength, like K parameter. You can see for K equals to 1, which is very less. You can see like there is no synchronicity at all, right? All oscillators are doing their own thing. Yeah. When K of them are already aligned together, but few of them are out of sync. Guys who are out of sync. These are the guys. There are some outside of the union. Okay. But when you increase k equals to 12, you can see all of them are together. They are behaving in unity. Okay. So this is exactly what you see in networks of oscillators. Okay. So to model this, all this circle phenomena and all these things, like theta is the angle, how the angle changes with time. So if all the I is a node, okay, I is an oscillator node, okay. So how many oscillators were there? Say 100. So you have d theta 1, d theta 2, so on till d theta 100. Okay. And you see the dynamics, how it is changing. Okay. So you can see this equation, don't worry about it. Okay. That's just the mathematical part. If you want to go deep, we can explain it later. But this is the simplest model of any coupled oscillator. Fine. So you see how the angle is varying with time. That's it. How the angle is varying with time. And yeah, if all are together in sync, then the angles must be almost the same. Okay. So this is just a model I want to say before doing any figure, because he's the first guy who derived all the synchronous and synchronization phenomenon. Yeah. So there are bit of math in it, but he also showed that you can get these spiral waves and different kinds of these patterns, chimeras and waves in just considering different lattices of that model. Okay, fine. So let us be back. Yeah. So these are all the videos so far. Any issues till now? Any? How many you are taking machine learning with graphs? Yeah, three of you are taking machine learning with graphs. Yes. So there you must have seen about graphs. What is a graph? What is a graph? Graph is nothing but a network. It's other way of like saying a network. What is a graph, anyone? What is a graph? Anyone? Yes. So it's a structure comprising of nodes and vertices. Sorry, nodes and edges. Yes. And there you find the adjacency matrix, the degree of a node, how many of each node is connected to the nearby nodes, and all those fact. Okay. Why it is necessary? Why you need to understand a network, first of all? If you see the households, there are many households, and each household is getting electric power. Okay, but that electric power is coming from a particular power grid, and it is not coming from a single main power grid, it is coming from a sub power grid. It is a substation. Okay, so how these are connected to each households and how the power is transmitted, if you understand that network, then you can understand that why, if your in a house in your power in your house is not there, that also implies that power won't be there in a nearby house, isn't it? If you see your house has no power, it might be the fuse, but one case, but other case is it might be that one full phase is not there, the substation is not giving that power is disconnected. Okay, so it is important to understand the power grids. So why it is important is in Germany, like I'll tell you one example. It has not happened in India yet because they are managing it quite carefully. But in Germany, what happened is there was a huge power and people could not understand how they could revamp that. Okay, they came to know that yes, we have to understand the network structure. Yes, like there is a software in Python which you can try that is known as Network X. Network X. So just search for Network X, and there you can see the power of networks. What kind of networks are there? What is random network? What is a small world network? Okay. So what they say is take any of you and take any person in the world. Take any person in the world, you will find that in order to connect from that person to the other person, other unknown person, you need maximum of 6 connections. You need just a maximum of 6 connections. You can find how you will do that. See, if you take me for an example and um, someone from the US, for example. Okay, so and I don't know that person. I don't know his name. I don't know the identity of that person, but I can still find 6 connections, maximum 6 connections through which I can find the name of that guy. Okay, how? Like I will talk to one of my friend who lives in US. Okay, fine. He's the node. So I got into US in the first instance. Okay, then what I will do, I will talk to that guy, see this photo, find me this guy. Okay, then he will say, okay, this guy, then he'll arrange, okay, he is from this state. Then he will see, he'll call his friend who is in that state. Okay, then he will go to that. Then slowly, it happened. Okay, then someone might be knowing, and they will know the connection over there. Okay, so this is, I think, 6 degrees of freedom. You can search. This is a huge concept of 6 degrees of freedom. Fine. So, and it's also saying, like, take you for example, in the world there will be seven like you, isn't it? Have you heard? No, you have heard. What is it called? I don't remember. Hmm? Anyway, so I will give you some of the works which motivated me to pursue. Just some snapshots. So this I did during my masters. This work I did during my masters. So there I came to know about all this phenomena of synchronization. Okay, so you can see what I did is in collaboration with the School of Electronics, the Department of Electronics and Communication. So I think some of you gave talk on Chua circuit. Okay, so you can see what I did is I connected all the Chua circuit in star connected network. Do you know what is star connection? I think in computer science, I think cyber security, people can know. Have you ever encountered star connection in cyber security? No? Okay. What happens is usually when they do an exam, think they are doing a competitive exam. There is one center, okay, and there are sub centers or schools where they are planning to have that exam. That center distributes the internet connection, that LAN connection to open their software. Okay, so there should be a center node and there should be some hub nodes which can connect the information and transmit the information. Okay, so this is why I got motivated to connect by Chua circuit. Okay, mainly because take for military purpose, like you have a central military hub, and there are different parts of the country near the border where the military needs to be strong. Okay, and the center hub needs to transmit information. So how they can transmit? And some of you already know that these chaotic systems are very nicely used for communication, secure communication. Okay, so you can see that if this happens, the Chua circuit is used because it shows chaos. It can be used for secure communication from both of the ends. So these are the things here. I will just write some parts. I think who took the Chua circuit? Chua circuit. Raise a hand. Yes. Yeah. So this I hope that you remember the dynamical equations of the Chua circuit. Anyway, so these are written down in terms of the electronic circuit equations. So I hope that you don't see normally these guys, okay? Because my one of my colleague is from electronics, so he actually found out all these. Yeah, he actually found out all these phenomena. So how this is a capacitor, C is a capacitor, R is a resistor, and L is an inductor. Okay. So how these all are connected to give you the chaotic phenomena is quite interesting. And Chua circuit has been the simplest circuit to show chaos. Simplest circuit which you can make it as a box and supply some battery power to it, and the output current you will get is chaos. Okay. I don't know. I should taste that thing. How it tastes. Like you can do the experiment. Has anyone tested current? No, don't test this current. It's very dangerous. But through lemon, you can do it. Has anyone done it? No? No? Shall I tell or not tell? Let me not tell. Might be dangerous. But I'll tell. So this is science experiment, which I have been doing as a kid. Okay, what I did is I saw some videos. So they take a lemon over half lemon, okay? And what you put is two copper wires. Two copper wires. Okay, just two copper wires. Fine. Just taste it. Just put it in your tongue. Those copper wire in your tongue, and then you will see it, slight tingling. You will feel some nerves is getting twitched. Okay, so it is generating some current. Okay, it is generating some current. Why that is happening? Because lemon has some electrolyte in it. Lemon has some electrolyte. Okay, due to that connection, this is something known as a electrochemical reaction, electrolysis or something like that. And due to that, these copper wires, they give you tingy taste. Okay, the copper wire you put, one copper wire you put in 1 ton, then take another copper wire, just touch it, remove it. Then you can feel it. Okay, or before doing it, you can watch any videos on YouTube to try it. Okay, yeah, it truly happens. What? Anyway, anyway, so you can, how we can couple them, how we can couple all these circuits in a star coupling. These lines you are seeing is a coupling. Okay, what is this coupling made up of? You can see that this is the coupling equation. You are pairing xj and xi, so you can see how they are coupled. Okay, this is known as a diffusive coupling. Don't worry about the term. It means that the same x state will be there. If it is xj minus yi, two dissimilar variables, these are known as conjugate coupling. And if you take the mean of those variables, it is known as mean field coupling. So many things are there. But anyway, so this is the coupling, and this is just the plot of one oscillator of the Chua circuit. Okay, in the network, not the single one. Okay, and you can see that here, not that of a good image. Um, so you can see that I plot the fourth node and I plot the third node. Right? And mostly it is behaving like a 45-degree line, but with some noise in it. Okay, but if you see the fourth node and the fifth node, they're perfectly aligned on a straight line. That means this guy is showing synchronization. Okay, is showing synchronization. However, this is kind of a partial synchronization. Like it has not attained sync quite clearly yet. Okay. So these are just two examples. So this was my master thesis, which I did at that time. And after that, I got more interested towards this topic, like how I can pursue this topic. Okay. Anyway, so um, yeah, so this motivated me. This I'm just telling my journey here, like how this helped me to understand these topics and move ahead. Okay, so after I did this, then after a few years, it came to my mind that why only star connection should be there. Okay, why this connection should be there? Why not? Why not? Why not? This can interact as well. Interact as well. Why not these can interact as well? If we do that, then can you see that this is a ring, this is a ring, and this was a star. Okay, so together they are known as ring star network. Star network, which I think Miss Arya and group are studying right now. Okay, so yeah, this is what was a study done with one colleague, where we are studying chimera states. What is a chimera? Anyone knows chimera? Anyone knows chimera? What is chimera? Chimera. Yeah. What is chimera? Yes. Yes. So that's a technical definition. That's a technical definition. But you will see that chimera actually meant something else. Chimera actually meant something else. Okay. So what it meant, we'll see. Anyway, so as you know, as I will tell you, chimera is this is the technical definition. Chimera states are something characterized by the coexistence. Like together, there will be synchronous as well as asynchronous states in your network. That means out of 100 people, like out